Hi, welcome to my video. This is Santanu Santra. So today I will discuss about the first law of thermodynamics. So the first law of thermodynamics, it was originated from the quantitative relationship between heat and work. So, if in a process in which either the amount of heat is produced that will be proportional to the work spent, or if there is some kind of work spent or work obtained, then that work will be proportional to the heat disappeared. That means the first law of thermodynamics is nothing but the Clausius statement. We can say that Clausius statement. So according to Clausius, the total energy of the universe is constant. The total energy of universe is constant. This is the first law. But this can be expressed with different statements. Postulate 1. That energy can neither be created nor be destroyed, but it can be converted from one kind to another kind. One kind to another kind. That means only the transfer of energy is possible, but that energy cannot be created nor be destroyed. Postulate 2. If one form of energy is disappeared, then exactly equivalent amount of energy in some other form will make its appearance. That means suppose in one process some kind of energy is disappearing, then equivalent amount of another kind of energy will appear. Postulate 3. Postulate 3. The energy of an isolated system will be constant. That means for a isolated system, this is surroundings, then there is no mass transfer is possible and no energy transfer is possible. So the total energy of the isolated system will be constant. And postulate 4. It is never possible to construct a perpetual motion machine. That means perpetual motion machine creation is not possible. What is perpetual motion machine? That can produce work without consuming any heat. That means it is not taking heat but it is producing work. That kind of machine construction is not possible. So suppose, so we want to derive the mathematical formula, mathematical expression for first law. It means how we can express this law mathematically. Suppose there is an initial state having internal energy Ui. I stands for initial, and it is undergoing to the final state having internal energy UF. F stands for final. Suppose during this conversion the system is absorbing heat from the surroundings. So as heat is absorbing, so according to IUPAC it is positive, and after absorption of Q amount of heat the system is doing some work. That means the work is done by the system. Work is done by the system. So according to IUPAC, this is negative, and it goes to the final state UF. So according to this first law of thermodynamics, the total energy of the universe is constant. That means we can say that the energy of initial state equal to energy in the final state, right? So energy in the initial state is Ui, and energy is the final state is, so energy in the initial state Ui, and it is taking some amount of heat Q. So before going to the final state, the total energy of the system is Ui plus Q, and after the transformation, the energy of the system UF, and the system do some work, that means amount of work. So we can say that UF minus Ui equal to Q plus W, or this is the change in internal energy, del U equal to Q plus W. This is the mathematical expression for the first law of thermodynamics, or for the small change we can write as du equal to dq plus dw. Or if we are considering mechanical work, then du equal to dq and dw equal to minus p external into dv. So this also can be considered if it is mechanical work and for small changes instead. Now we are talking about a new function, enthalpy, ENTHALPY. So if I see in the laboratory, most of the chemical processes are taking place in constant pressure condition, or we can say at isobaric condition. So in that case, if we want to calculate the energy changes of these processes, so we have to take the help of a new function, and that is the enthalpy. Suppose for a closed system, suppose we are considering one closed system, and from the first law of thermodynamics we can write as du equal to dq plus dw, or we can write as du equal to dq minus p external into dv. If there is a reversible change, then P P external equal to P internal plus minus dP, or we can say that P external nearly equal to P internal. That means we can write for reversible closed system, the first law will be write du equal to dq minus pdv. Right? So this we can say that equation number 1. Now if we are considering like that, the d of pv, I mean for the small change in the value of pv, we can write as pdv plus vdp plus dp into dv. And most of the case we write only these two terms because this is negligible term, as this is the product of two infinitesimal quantities. So this is, we can write as pdv plus vdp. Right? Now if we add this with this, then it becomes d of u plus pv, then dq minus pdv plus pdv plus vdp. Right? Or we can say that du plus pv equal to dq, this will be cancelled, plus vdp. This we can say that equation number 2. So now we are defining a new state function. How? We know that u is a state function, p is a state function, v is a state function. So definitely the multiplication pv will be a state function, and if we add a state function with another state function, this will result in another state function. So the state function h is a new function which is defined as u plus pv. Right? So we can say that from that equation dh equal to dq plus vdv. So enthalpy, this is the enthalpy, this is the enthalpy, or we can term it as heat content. Heat content. That H equal to U plus PV and DH equal to DQ plus VDP. Right? This we can term as equation number 3. Now, at constant pressure, as most of the cases in laboratory, this condition, at constant pressure dP equal to 0, so dH at constant pressure equal to dQ at constant pressure. So we can write as dH will be equal to dQ constant pressure. That means if we see very closely to that equation, there is a lots of significance behind this equation. That I already told earlier that Q, heat change, is a path function, right? So dQ can never be a perfect differential, but here H, enthalpy, is a state function. That means dH is a perfect differential. So how a perfect differential can be equal to a imperfect differential? That means only in that condition, that under the constant pressure condition, that dq has to be a perfect differential in order to validate this equation. That means if someone question you ask you that under which condition dq becomes a perfect differential, or under which condition heat change will be a state function, then you can say that at constant pressure dp equal to 0, so then dh equal to dq constant pressure. So at this condition dq constant pressure is a perfect differential, and that is why q is a state function. Now we will talk about Joule's free expansion experiment. Right? Joule's free expansion experiment. Joule took two bulbs. This is one bulb and this is another bulb, joined by a connecting tube and covered by a stopcock, or attached with a stopcock. This is the coil. We can control the passage of matter through the connecting tube. One is filled with gas at a high pressure and another is in vacuum, or we can say that evacuated condition, and the whole experiment is carried out under isothermal condition, and no heat passage is allowed here. That means the wall is adiabatic. The wall is adiabatic. This is adiabatic wall. And this is taken in a beaker dipped in water. So that the isothermality can preserve, and one temperature recorded thermometer is taken, and one stirrer is taken. Okay, so this is the apparatus for Joule's experiment. Now what happened? So the stopcock is opened, then the gas expands through the connecting tube, until both the bulbs are uniformly occupied. So as the system is covered by adiabatic wall, no heat transfer is possible. No heat has been supplied. Right? So dq equal to 0. Now we can say that as dq is 0, then this is an adiabatic expansion. Right? Here gas expand at constant q. That means we can write as adiabatic expansion. Now this is the condition where constant temperature bath is used for that experiment. That means the whole experiment is carried out at thermostat. That means the temperature change will be 0. How? Suppose dW for small change in work, we can write as minus P external into dV, right? Now, as the gas expand against zero opposing pressure, this is fully evacuated. So P external equal to 0. So work will be 0. Now, according to first law of thermodynamics, we can write as du equal to dq plus dw, right? So dq equal to 0, dw equal to 0, so du must be 0, and we know that u is the function of temperature. As du is 0, then dt must be 0. dt must be 0. That means the temperature remains constant. That means we can say that this is isothermal. So the free expansion is a process which is isothermal as well as adiabatic. Now we know that U is the function of temperature and volume, right? So we can write du equal to del U del T constant volume into dt plus del U del V constant temperature into dV. Now as dt equal to 0 and du equal to 0, we already proved du equal to 0, then dt equal to 0, then you can say that this term must be 0, or del u del v constant t into dv equal to 0. As dv not equal to 0 because there is a expansion of volume, so dv not equal to 0, then del u del v constant t equal to 0. This is the condition for free expansion, that del u del v constant t equal to 0. Now we can write as del u del v constant t equal to del u del p constant t into del p del v constant t. So this is 0, right? Now del p del v constant t, del p del v constant t not equal to 0, it is always negative. If at constant temperature volume is increases, then pressure decreases, or if pressure increases, then volume decreases. So we can write as del u del p constant t equal to 0. This is also one condition for free expansion, that del u del v constant t equal to 0 or del u del p constant t equal to 0. So we already proved that del u del v constant t equal to 0 and del u del p constant t equal to 0, right? Now we can write as enthalpy H equal to U plus PV. So differentiating this equation with respect to P at constant temperature, equal to del U del P constant temperature plus del PV del P constant temperature. Now we already proved that del U del P constant T equal to 0. Now for an ideal gas, at constant temperature PV equal to constant. So differentiating a constant term with respect to pressure will always produce 0, then this term also produce 0, then del H del P constant T equal to 0. Right? Again, if del H del P constant T equal to 0, then del H del V constant T into del V del P constant T equal to 0. Multiply. So, we know that del V del P constant T not equal to 0. Then del H del V constant T equal to 0. So, this is the condition, this is the condition, this is the condition, and this is the condition. So, for a free expansion process, these four conditions will be satisfied. Right? Now, molar heat capacity. Where to write? Here. Molar heat capacity. Right? So, what is specific heat? We have to know at first what is specific heat. Specific heat of a substance is the amount of heat required to raise the temperature of